A researcher has vanished under mysterious circumstances, leaving behind only a cryptic message. The answers are hidden, not where they should be, but where no one dares to look. An unnamed agent steps into the shadows, retracing the scientist's steps, uncovering a deep flaw in AI models, one that could change the way we understand machine learning forever. In this video, we're diving deep into the world of transformer-encoder architectures, exposing the hidden layers that most models ignore. We'll reveal why final layer outputs might not be telling the full story and how AI models like BERT and SHACT capture deeper linguistic structures than we ever imagined. This is more than just an analysis of AI. It's an investigation into the future of natural language processing and what researchers are only beginning to uncover. Are you ready to unlock the secrets buried inside the machine? Let's begin. I've been assigned a peculiar case. A researcher working at the forefront of artificial intelligence has vanished, leaving behind a trail of fragmented notes and one haunting clue. The answers are hidden, not where they should be, but where no one dares to look. That's where my investigation begins, inside the enigmatic world of transformer-encoder architectures. These architectures are at the very core of modern natural language processing. They're designed to process sequential data, like sentences or documents, by capturing the contextual relationships between words. Imagine this as a machine learning model equipped with the power to not only understand the individual meanings of words, but also how these meanings shift and evolve depending on their context. It's like teaching a machine not just the meaning of apple, but also what it signifies. In the sentence, "She bought an apple to share with her teacher." At the heart of these systems lies a mechanism called self-attention. This allows the model to weigh the importance of each word in a sentence relative to every other word, effectively enhancing its ability to grasp the meaning of the entire context. This self-attention is what makes models like Gemini, DeepSeek, or GPT so powerful. But the story doesn't end there. There's more happening beneath the surface. This pre-training process generates what we call contextualized word embeddings, dynamic representations that shift and adapt based on surrounding words. For tasks like named entity recognition or even chunking phrases into meaningful units, these embeddings are critical. They bring models closer to understanding language in the way humans do. But my question is, could we be missing something deeper that lies hidden in the architecture itself? Today, I'll take you through this mystery step by step. Together, we'll uncover the hidden layers of these models, learn how they process language, and why some of their secrets might be slipping through the cracks. This isn't just a technical dive. It's a journey into the unknown, and I'm here to guide you. As I dig deeper into the researcher's trail, I come across a fascinating clue, a reference to something called contextualized word embeddings. It seems to be a cornerstone of their work, and understanding it might lead me closer to unraveling this mystery. Contextualized word embeddings are the building blocks of modern transformer models like BERT. These embeddings are not static. They evolve and adapt based on the surrounding text. Think of them as dynamic representations of words. For example, the word bank can mean the side of a river or a financial institution, and it's the context around the word that helps us understand its true meaning. Transformer models process this context by leveraging multiple layers of self-attention mechanisms, which allow them to evaluate every word in relation to every other word in a sentence. Each token in the input sequence is represented as a vector, a mathematical construct that shifts its positioning depending on the surrounding tokens. This adaptability is what makes these embeddings so powerful. They allow models to process both the syntactic and semantic relationships within language. It's like giving the model the ability to see not just individual puzzle pieces, but how they fit together to form the bigger picture. The researcher seemed obsessed with this mechanism, believing it held the key to solving some of the deepest challenges in natural language processing. But there's still a missing piece. Why focus so intently on these embeddings? Is there something hidden in how they're processed? Something overlooked by everyone else? I keep searching, following the breadcrumbs they've left behind. The answers lie deeper within the layers of these transformer encoders waiting to be uncovered. As I push further into the researcher's notes, one term begins to surface repeatedly: span recognition. At first, it seems like just another technical phrase, but the deeper I look, the more I realize it's central to everything they were working on. Span recognition, I learn, is a critical task in natural language processing. It's the ability of a model to not just read and understand a text, but to actively identify and classify specific segments of that text. These segments might include names of people, places, or even complex noun phrases like the tallest building in New York. It's like teaching a machine to comb through a document and highlight exactly what's important. The researchers' focus was on transformer encoder models like BERT and BioBERT, which excel at this kind of precision. These models generate rich contextualized embeddings that are not only capable of understanding a word, but also its relationship with every other word in a sentence. Through these embeddings, transformer models can create latent syntactic vector spaces. This is essentially a map of how words connect and interact, making it possible for the model to group and classify spans with remarkable accuracy. But how do we know these models work as well as we hope? The researchers' work delved into evaluation metrics like recall and the F1 score. Recall measures the ability of the model to find all the relevant spans in a dataset, almost like a detective ensuring every clue is uncovered. F1 score, on the other hand, balances this ability with precision, making sure the spans identified are accurate and meaningful. One of the models the researcher evaluated achieved an extraordinary 97.37% recall on the Genia dataset. That's almost every single relevant span correctly identified. Imagine the potential of this level of accuracy in fields like medicine, where identifying critical terms in research papers or patient records could save lives. However, this wasn't just about numbers for the researcher. Their notes suggest they were striving for more, pushing the boundaries of what span recognition models could achieve. I begin to wonder, why the fixation? What were they trying to solve? As I pore over their notes, I start to uncover hints of a larger problem, one that ties directly to how these spans are structured and recognized. It's not just about recognizing flat, simple spans like John Smith. There's a deeper challenge: nested spans, overlapping entities, and other complexities that even state-of-the-art models struggle to handle. And yet, despite the remarkable progress demonstrated by the recall and F1 scores, something was still missing. The researchers' notes grow more fragmented, more desperate, as though they were chasing a breakthrough but couldn't quite reach it. Was it frustration? Or were they on the brink of uncovering a flaw, one buried deep within the layers of these models? These questions continue to haunt me as I sift through the data, tracing the researchers' path. Whatever they discovered, I know it's tied to this: span recognition and the hidden intricacies of how transformer models process language. The answers are out there, hidden within the data, waiting to be revealed. The deeper I delve into the researchers' work, the clearer it becomes that something was troubling them, a blind spot in the models they were studying. At first glance, transformer encoders seem like marvels of modern technology, capable of handling language with astonishing accuracy. But as I trace the researchers' steps, I uncover a startling realization. The final layers of these models, the ones we rely on for predictions, might be missing something critical. Their notes talk about a concept that feels almost paradoxical. While the final layers are optimized for specific tasks, they often sacrifice comprehensive understanding. It's like focusing only on the polished results of a puzzle while ignoring the intricate connections between its individual pieces. Important insights, deeply embedded in the intermediate layers of the model, can get lost. The researcher described this as a problem of overlooking valuable information. You see, these intermediate layers aren't just stepping stones to the final output. They hold rich, contextualized vectors that capture intricate relationships and patterns within the data. These hidden representations can reveal the full complexity of linguistic structures, mapping how words, phrases, and ideas connect across a sentence. But here's the catch. If we rely solely on the final output, much of this depth is flattened, simplified, or even discarded. The researchers' notes seemed to obsess over these intermediate representations, describing them as a treasure trove of untapped potential. They believed that the final layer, while optimized for tasks like classification, was ultimately limited, trained to focus on specific goals rather than offering a complete understanding of the data. It's like using a spotlight to illuminate only one part of a room while the rest remains in the shadows. What strikes me is how urgent their writing became when addressing this challenge. They saw these hidden layers as more than just data. They were clues waiting to be uncovered, holding the answers to why models sometimes fail to grasp complex linguistic patterns. Think of nested phrases, overlapping entities, or subtle shifts in meaning across contexts. These are the nuances that intermediate layers can capture, but final outputs can miss. As I try to connect the dots, one question keeps resurfacing. What was the researcher seeing that others ignored? Did they believe these hidden layers held the key to solving the deeper challenges in NLP? Or were they uncovering a flaw so fundamental it could shift the way we think about transformer-encoder architectures? Their trail leads me to one undeniable conclusion. There's more happening beneath the surface than meets the eye. The final layers may offer polished results, but the true understanding of language, the subtle complexities, and the deeper connections lie buried in the intermediate layers. And now, I'm determined to uncover what the researcher saw in those layers, hidden in plain sight. The further I dive into the researcher's trail, the more one word stands out, a model called SHACT. It feels like the centerpiece of their work, the culmination of everything they were trying to solve. SHACT, or syntactic hierarchical agglomerative clustering, is a model designed to go deeper than anything I've encountered before. It doesn't just recognize words or spans. It strives to disentangle the very fabric of language, splitting syntactic structures from semantic meaning in a way that allows for clarity and precision. The researchers' notes describe this as a revolutionary step forward. SHACT takes the hidden representations of transformer-encoder architectures and projects them into a latent vector space where it clusters tokens based on their syntactic roles. Imagine words and phrases being grouped into tightly bound clusters, like planets orbiting their own stars. These clusters make it easier for the model to identify patterns, relationships, and even overlapping entities that standard models struggle with. But what sets SHACT apart is its purpose of disentanglement. Traditional transformer models often blend syntactic and semantic information, muddying the waters when it comes to analyzing complex sentences. SHACT, on the other hand, focuses on separating these two layers of meaning. By minimizing the distance between tokens within the same span and maximizing the distance from unrelated tokens, SHACT creates clearer and more defined clusters. It's like organizing a cluttered library into perfectly categorized shelves where every book is exactly where it belongs. The applications of this are staggering. SHACT excels in tasks like nested and flat-named entity recognition, where entities can overlap or exist within one another. Think of a sentence like, John Smith, a professor at Harvard University, wrote a paper on machine learning. Models like SHACT can identify not just John Smith and Harvard University as individual entities, but also see how professor ties into the larger structure. It's this ability to handle complexity that sets SHACT apart. The researchers' evaluations showed just how powerful SHACT could be. It achieved competitive results on benchmarks like the GENIA, CoNLL 2003, and CoNLL 2000 datasets, significantly improving classification accuracy in span recognition tasks. Yet, their notes suggest they weren't satisfied. They believed SHACT was just the beginning, a glimpse of what's possible if we fully embrace the potential of transformer encoders. As I piece this together, I start to see why the researcher was so consumed by this work. SHACT isn't just a tool, it's a new way of understanding language, a model designed to break free from the limitations of traditional approaches. But there's still a lingering question. What challenges did they face? Was SHACT the solution they hoped for, or did it reveal an even deeper problem? That's the mystery I'm determined to solve. As I dive further into the researchers' work, I find myself staring at what feels like the blueprint of their obsession, the loss function. If SHACT was their masterpiece, this loss function was the heart of it, the mechanism driving its ability to disentangle meaning and structure. The researcher referred to it as LZIN, and their notes described it as both simple and elegant. But what it does is anything but ordinary. The goal of this loss function is to optimize the projection of token representations into a latent space, enabling the model to separate syntactic structures from semantic meaning. Imagine taking a crowded room full of conversations and somehow isolating each one, separating the people who are part of the same discussion while distancing unrelated groups. That's exactly what this function does for language. It groups related tokens closely together while pushing apart those that don't belong. Mathematically, it's defined as LSIN D N Gasser ICD ECD. At first glance, it's just a formula, but breaking it down reveals the brilliance behind it. ICD stands for intracluster distance, which is the maximum distance between tokens within the same span. The goal here is to minimize it, ensuring that tokens belonging to the same cluster are as close together as possible. ECD, on the other hand, is the extra-cluster distance, the minimum distance between tokens in a span and those outside it. The goal here is the opposite, to maximize it, creating a clear separation between relevant and non-relevant tokens. This balance between pulling tokens together and pushing them apart is what gives SHACT its ability to classify spans so accurately. The loss function ensures that the clusters formed in the latent space aren't just arbitrary, they're meaningful, representing the underlying structure of the language. It's like sculpting a perfect map where every point has its place and no detail is left to chance. The researchers' notes describe how this function was key to solving the most challenging tasks in span recognition. Nested entities, overlapping phrases, and other complex structures could finally be handled with precision, all because of this carefully designed function. Yet, they also hinted at the difficulty of fine-tuning it. Too much weight on one side, and the model loses clarity. Too little, and the clusters become messy and indistinct. As I try to piece together the significance of this function, I can't help but feel that it's a pivotal part of the mystery. The researchers saw it as more than a mathematical tool. They believed it was the key to unlocking the full potential of transformer models. But there's still a nagging question. If this function works so well, why did their notes suggest frustration? Were they pushing against the limits of what even this function could achieve? Or was there something deeper in the architecture itself that they couldn't resolve? For now, I know one thing. This loss function was central to their work, a foundation on which they built their vision for disentangling language. But whether it was enough to solve their mystery, that's something I still need to uncover. The deeper I dive into the researchers' work, the clearer it becomes that everything hinges on one critical process, the methodology they use to unlock the potential of hidden representations. Their notes detail a step-by-step process called hierarchical agglomerative clustering, or HACK, and it feels like the framework of their obsession. This process wasn't just a tool, it was the mechanism driving their quest to disentangle the complex relationships between tokens and spans. HACK begins with the raw material, the hidden representations of tokens extracted from transformer encoder layers. These representations are more than just data points. They're rich vectors that capture both the syntactic and semantic nuances of language, forming the foundation for everything that follows. Imagine starting with a series of interconnected threads, each one representing how words relate to one another. HACK's job is to sort and cluster these threads into coherent groups. The first step in the process is distance calculation. It's here that the model determines how closely related tokens are to one another in the latent space. Think of it as measuring the strength of connections in a web of words. Words that share a strong syntactic or semantic relationship are kept closer, while unrelated ones are pushed further apart. This step sets the stage for the next crucial phase, clustering. In this phase, HACK groups tokens into hierarchical structures based on their calculated distances. Tokens are merged into clusters, creating a binary tree where each node represents a group of syntactically related words. Picture this as building a family tree of language where every branch and connection reflects the relationships between tokens. It's this hierarchical structure that allows the model to identify even the most complex linguistic patterns. From here, the process moves to candidate span generation. Each merge operation within the binary tree corresponds to a potential span. This is where SHACT truly shines, by identifying not just simple spans, but also multi-word entities and overlapping structures. Tasks like nested named entity recognition, which have long been a challenge for traditional models, suddenly become manageable. HAC can recognize, for example, that New York is a location, New York Times is an organization, and both are valid spans depending on the context. The brilliance of HACK lies in how it integrates each of these steps into a seamless process. It takes raw token representations and transforms them into structured clusters, extracting meaning and relationships that were once hidden beneath the surface. But as I study this process, I begin to see why the researcher was so consumed by it. HACI is powerful, but it's also fragile. Every step relies on precise calculations, and even a small error in one phase can ripple through the rest, leading to misclassifications or lost spans. It's clear to me now that Schacht was at the center of their work, the mechanism through which they hope to unravel the mysteries of language. But the more I study it, the more questions arise. Did HACK give them the clarity they were searching for, or did it reveal new layers of complexity they hadn't anticipated? And why did they seem so determined to push this process further, as if something vital was still missing? These are the questions I'll need to answer as I continue to follow their trail. But for now, one thing is certain. HACK wasn't just a step in their research. It was their attempt to map the uncharted territory of language, one cluster at a time. As I continue piecing together the researchers' work, I find myself drawn to their evaluations, their meticulous attempt to measure the success of what they had built. Slide after slide of notes, diagrams, and tables reveal the metrics they used to analyze their model's performance. This was no ordinary assessment. It was an effort to quantify the very essence of what made SHACT effective. At the heart of it all were three key measures: precision, recall, and the F1 score. Let's start with precision. Precision measures how accurate the model is in its predictions. In simpler terms, it asks, of all the spans the model identified, how many were actually correct? High precision means the model is effective at recognizing the right spans without misclassifying irrelevant ones. The researcher saw precision as a measure of the model's ability to stay focused, to pinpoint the true meaning in a sea of potential interpretations. But precision alone wasn't enough. That's where recall comes in. Recall measures the model's ability to identify all the relevant spans within a dataset. It asks a different question. Of all the spans that should have been identified, how many did the model actually catch? Think of it like a detective trying to find every clue at a crime scene. A high recall score means fewer critical spans were missed, which is especially vital in applications like medical text analysis, where missing key terms could have real-world consequences. SHACT's recall rates were stunning: 96.44% on CoNLL 2000, 92.12% on CoNLL 2003, and 78.31% on Genia. These numbers tell a story of remarkable success, but I can't help but wonder why the Genia dataset posed a greater challenge. Finally, there's the F1 score, a harmonic balance between precision and recall. It's the metric that asks, how well does the model perform overall, considering both accuracy and completeness? The researchers' evaluations showed that SHACT excelled in this regard, with an F1 score of 79.76 in nested named entity recognition on Genia and 91.74 in flat NER on CoNLL 2003. These numbers reflected the model's capability to handle both simple and complex spans, bridging the gap between traditional and advanced NLP tasks. But as I pore over these results, I noticed something strange in the researchers' notes. They weren't just celebrating these scores, they were questioning them. Despite the high metrics, they kept asking, what are we missing? Where do errors come from? Their focus shifted to the points where the model fell short, the cases where misclassifications occurred, or where the model failed to separate overlapping entities. Their questions lead me to a deeper understanding of their frustration. The metrics told one part of the story, but the researchers seemed to believe that the real insights lay in the errors. Precision, recall, and F1 scores could measure performance, but they couldn't fully explain why the model succeeded or failed in specific instances. It was this pursuit of understanding that drove them to push SHACT even further, to refine its ability to handle complexity and to uncover the layers of meaning still hidden beneath the surface. As I step back from these metrics, I find myself asking the same questions they must have. If these scores are so strong, why does the work feel unfinished? What truths did the researchers see in the gaps between the numbers? And how far can this pursuit of perfection really take us? As I dig deeper into the researchers' notes, I find myself in a room filled with comparisons, charts, tables, and scribbled thoughts about where SHACT stands among other state-of-the-art models. It's here that I begin to see the bigger picture. The researcher wasn't just trying to build a model that worked, they were trying to surpass the limits of what was already possible. SHACT's performance speaks for itself. On the Genia dataset, it achieved an F1 score of 79.76 in nested named entity recognition, a task that challenges models to identify overlapping entities and complex linguistic structures. That score was competitive with leading models like Shen et al., which achieved 81.77, and Tan et al., which scored 78.3. But SHACT didn't stop there. With a recall rate of 97.37%, it demonstrated an extraordinary ability to identify relevant spans, setting a benchmark in clustering nested syntactic representations. Yet, when compared to models designed for flat NER tasks, SHACT faced stiff competition. For instance, models like Devlin et al.'s BERT achieved an F1 score of 92.8, and Wang et al.'s work pushed it even further to 94.6. These state-of-the-art models were better tuned for simpler, non-overlapping structures, which gave them an edge in these tasks. SHACT, on the other hand, was designed for complexity, for cases where entities overlap, nest, or exist in hierarchical relationships. This trade-off was intentional, but it came with its own set of challenges. What struck me most in the researchers' notes wasn't just the celebration of SHACT's strengths, it was their relentless focus on its weaknesses. They recognized that while SHACT excelled at disentangling nested structures, there was still room for improvement in the classification phase. This was especially evident when aligning the results of SHACT's hierarchical clustering process with standard NER benchmarks. The researchers seemed frustrated by the gap, noting that even a small misstep in classification could cascade into errors that undermine the overall performance. And yet, it wasn't just about metrics. The notes reflected a deeper question: what comes next? The researcher was acutely aware that models like SHACT represent an evolution in natural language processing, but not its endpoint. They believed there was more to uncover, especially when it came to bridging the gap between models designed for simplicity and those capable of handling true complexity. As I sift through the comparisons, one thing becomes clear. This wasn't just a technical exercise for the researcher. It was a quest to push the boundaries of what NLP models could achieve. They wanted to create something that wasn't just better, it was smarter, more adaptable, more aligned with the nuances of human language. But whether Schacht succeeded in fulfilling that vision remains an open question, one I'll have to answer as I follow their trail. For now, I'm left with one undeniable truth. Schacht stands as a testament to what's possible when we aim to solve the hardest problems in language processing. But it also highlights the ongoing challenges in building models that don't just work but truly understand. That's the line the researcher was trying to walk, a line between the limits of today and the possibilities of tomorrow. As I delve further into the evaluation of Schacht, the researcher's focus becomes unmistakably clear. It wasn't enough to simply build a model that worked. They wanted to measure its ability to uncover hidden relationships within language, and they did so through rigorous intrinsic evaluation. The results were as fascinating as the process itself. The first breakthrough came with Schacht's clustering ability. By leveraging its ability to disentangle syntactic spans, Schacht demonstrated a remarkable recall of 97.37% on the Genia dataset. This number isn't just a statistic, it's a testament to the model's precision in grouping words and phrases into meaningful clusters. It's as though Schacht had developed a sixth sense for spotting the nuanced connections between tokens that even other advanced models missed. But the real test came when the researcher compared Schacht's performance against other vector representations. They evaluated three different approaches. The first, PLM Final, focused on final layer representations. While these are often optimized for downstream tasks, they yielded only a recall of 52.94%, underscoring how much information gets lost when intermediate layers are ignored. The second, PLM Full, concatenated all hidden representations and slightly improved recall to 51.51%, but it still fell short of Schacht. The last approach, L5 Random, used randomly initialized latent vectors and performed even worse, at 51.50%. The stark contrast between these methods and Schacht's performance highlighted the importance of its trained projection component in accurately capturing syntactic relationships. But there was more to the researchers' evaluation than numbers. They saw these results as proof of something larger, something the rest of the field had largely overlooked. Traditional transformer models, optimized for semantic understanding, often struggled with syntactic span clustering. The researchers' notes describe Schacht's approach as a paradigm shift. By optimizing the projection function to focus on syntax, Schacht didn't just match the performance of other models, it exceeded them in areas where they faltered. What's most striking in their analysis is the implications for syntactic analysis. The researcher noted that Schacht's ability to separate syntax from semantics had broad-reaching effects. It enhanced the model's ability to handle overlapping entities, nested spans, and other linguistic complexities, areas that traditional models often oversimplified. The significance of this goes beyond academic metrics. It represents a step forward in how we train models to understand language as we do, with all its subtleties and intricacies. Yet, as I study the researchers' findings, I sense that they weren't entirely satisfied. Their notes hint at challenges even Schacht couldn't overcome, cases where misclassifications persisted or where the model failed to disentangle meaning entirely. These limitations only seem to fuel their drive to push further. to refine SHACT into something even more powerful. As I reflect on these results, one thing becomes clear. SHACT's intrinsic evaluation was about more than measuring its success. It was about proving that language models could go deeper, uncovering layers of meaning and structure that had long been ignored. And while the researchers' journey with SHACT was far from over, it's clear that they had already reshaped the way we think about transformer architectures and their potential. As I continue to follow the researchers' work, I arrive at one of the most critical aspects of their journey, the extrinsic evaluation of SHACT. This wasn't just about metrics or comparisons. It was about testing the model in real-world scenarios to understand how well it could handle the diverse and complex challenges of natural language processing. The results were both impressive and revealing. SHACT was tested across 3 key tasks: flat-named entity recognition, NER, nested NER, and chunking. Each of these tasks posed unique challenges, and the results showed how versatile the model truly was. In flat-NER, where entities are straightforward and non-overlapping, SHACT achieved an F1 score of 91.74 on the CoNLL 2003 dataset. This placed it competitively against state-of-the-art models, though it lagged slightly behind those specialized for flat structures. Flat NER is a task where precision often takes precedence, and SHACT's ability to balance accuracy and recall proved to be one of its greatest strengths. But the real test came with nested NER, a task that involves identifying entities within entities, like recognizing John Smith as a person within the phrase John Smith, CEO of Tech Corp. This is where SHACT's architecture truly shone. On the JANIA dataset, it achieved an F1 score of 79.76, reflecting its ability to untangle overlapping and hierarchical structures. This performance highlighted SHACT's potential to handle complexity that most models struggle to grasp. In the chunking task, SHACT achieved one of its highest scores, a remarkable 96.61 F1 on the CoNLL 2000 dataset. Chunking involves grouping words into syntactic units like noun or verb phrases, which is crucial for understanding sentence structure. SHACT's performance in this area demonstrated its ability to classify and identify chunks with precision, further proving its adaptability across NLP applications. But what struck me most was the researchers' focus on error analysis. They didn't just celebrate SHACT's successes, they carefully dissected its failures. Their evaluations revealed that misclassification errors had the most significant impact on performance. For instance, while SHACT excelled at identifying spans, it sometimes struggled to assign the correct entity class, especially when spans overlapped or shared similar syntactic patterns. In one case, the model misclassified certain technical terms in nested entities, leading to gaps in recall. Despite these challenges, SHACT's architecture offered something rare: insight into why errors occurred. By separating syntactic and semantic analyses, the model allowed the researcher to pinpoint the origin of these errors. They noted that this transparency made SHACT not only a powerful tool for NLP, but also a model that could guide further iterations and improvements. It wasn't just a tool for solving problems, it was a tool for learning and evolving. As I study these evaluations, I realized that SHACT wasn't perfect, but it was ambitious. The researcher wasn't trying to create a flawless model. They were trying to push the boundaries of what's possible in NLP. These extrinsic evaluations were proof of its potential and a roadmap for what still needed to be done. The journey wasn't over, but it was clear that SHACT had already made a significant impact. For now, I'm left with one question. If SHACT could perform so well across these tasks, what was the researcher aiming for next? The answers lie deeper in their work, waiting to be uncovered. As I sift through the researchers' final notes, I find their focus narrowing to a crucial element of their work: error analysis and explainability. This wasn't just about identifying where SHACT succeeded or failed. It was about understanding why. To the researcher, these errors weren't setbacks. They were opportunities to refine the model, to learn from its limitations, and to push it closer to perfection. The first area they examined was common errors in SHACT. These errors fell into two broad categories: semantic and syntactic. Semantic errors occurred when the model correctly identified spans but failed to classify them correctly. For example, a span like human monocytes was clustered accurately but misclassified as null. It's like finding a puzzle piece and knowing it fits somewhere but placing it in the wrong spot. These errors often arose from overlapping or ambiguous spans where even slight nuances in the context could mislead the model. Then there were syntactic errors where certain spans were missing from the binary tree altogether. In one case, the span CD28 Moab was not included in the final prediction despite being present in the data. This pointed to a deeper issue in how Schacht's clustering process aligned with the syntactic structures of language. These errors weren't just about misclassification, they revealed gaps in how the model understood the relationships between tokens, showing the limits of its current approach. But the researcher didn't stop there. They analyzed the impact of error propagation and found that it had minimal effects on recall, ranging from 0.32% to 1.93%. This was a surprising insight. It suggested that while small errors could cascade through the system, their overall impact was limited. Instead, misclassification emerged as the more significant challenge. This finding shifted the focus toward improving how SHACT categorized spans rather than its ability to cluster them in the first place. What set SHACT apart, however, was its explainability. The model's architecture allowed for a clear separation between syntactic and semantic analyses, making it possible to trace errors back to their source. This level of transparency wasn't just useful for debugging, it offered insights into how the model thought. By analyzing the syntactic structures Schacht generated, the researcher could see where and why it made mistakes, turning those errors into actionable feedback for the next iteration. The researchers' notes hinted at something profound. Explainability wasn't just a feature of Schacht, it was a philosophy. They believed that models like Schacht shouldn't just solve problems, they should help us understand the nature of the problems themselves. By doing so, they could become tools for exploration, opening new doors in natural language processing and beyond. As I reflect on this, I see the researcher's journey in a new light. This wasn't about building a perfect model, it was about building a model that could grow, adapt, and improve. Schacht's errors weren't failures, they were steps towards something greater. And in this pursuit of explainability, the researcher wasn't just uncovering the limits of the model, they were uncovering the possibilities of the future. Now, the final question remains: where do we go from here? If Schacht can explain its own shortcomings, how can we use those explanations to push the boundaries even further? The answers lie ahead, in the work still to be done. As I reach the culmination of the researcher's work, I find myself staring at a summary of everything they built, learned, and envisioned for the future. This isn't just the end of a project, it's the beginning of a new chapter. The slide is labeled Conclusion and Future Work, and it serves as both a reflection and a roadmap. First, the key findings of Schacht. The researchers' work effectively disentangled syntactic structures from the hidden layers of transformer encoders, unlocking a new level of understanding in natural language processing. Schacht excelled in named entity recognition, NER, and chunking tasks, achieving F1 scores of 79.76 on Genia for nested NER and 91.74 on CoNLL 2003 for flat NER. For chunking, it reached an impressive 96.61 F1 on CoNLL 2000. These numbers represent more than just benchmarks. They're proof that Schacht wasn't just another model. It was a bold attempt to bridge the gap between surface-level understanding and the deeper complexities of language. But every success comes with challenges, and the researcher was keenly aware of them. One of the biggest issues was in the classification phase. Despite SHACT's ability to disentangle syntax and semantics, aligning its binary trees with full constituency trees remained difficult. This misalignment sometimes led to misclassifications, particularly in complex or ambiguous spans. The researcher viewed this as an area ripe for improvement in future iterations of the model. Then there's the significance of SHACT in NLP. By representing ground truth spans as clusters in a latent space, SHACT offers a way to analyze syntactic relationships that goes beyond traditional approaches. This isn't just about improving performance metrics. It's about enabling a deeper understanding of how language works. SHACT provides a tool for exploring the intricate web of relationships within text, helping researchers and practitioners alike to uncover patterns that were once hidden. But the slide doesn't just look back, it looks forward. The future research directions outlined by the researcher are ambitious, yet grounded in the work they've already done. They envisioned applying SHACT to other languages and syntactic structures, such as dependency trees, to broaden its applicability. They also proposed integrating more complex entity types to push the boundaries of span recognition further. These ideas suggest that SHACT was never meant to be a finished product. It was a foundation, a starting point for what's possible in transformer-based architectures. As I read these final notes, I can't help but feel the researchers' passion for their work. This wasn't just about building a better model, it was about advancing the field, about challenging what we think we know about language and the systems we use to process it. SHACT is more than a technical achievement. It's a testament to what's possible when we dare to push the boundaries, to tackle the hardest problems, and to imagine a future where language models don't just understand, they truly learn. And so, as I close this chapter, I find myself inspired by the researcher's vision. SHACT may have started as one model, but its impact will resonate far beyond its original design. The question now is, how will we take this work forward? How will we build on what the researcher achieved to create models that not only reflect the complexity of language, but help us understand it in ways we've never thought possible? Write me in the comment.